What's up guys, welcome back to the next video on learning mathematics. My name is QDS Dan and you guys watching my channel Croywood. Okay, so in this video we're gonna see the logical equivalence in the truth tables. Two molecular statements P and Q are logically equivalent provided P is true precisely when Q is true. That is, P and Q have the same truth value under any assignments of truth values to their atomic parts. To verify that the two statements are logically equivalent, you can make a truth table for each and check whether the columns for the two statements are identical. So we have here, and we're looking for equivalence here. If you guys looking here, that's P. We have a Q. P implies Q and not P or Q. So we have here is truth and true. It's P implies Q is true and not P or Q or is true, and true and false. P implies Q is false and not P or Q is false. So we have false and true. P is false and Q is true. P implies Q is true and not P or Q is true. So we have P false and Q false. P implies Q is true and not P or Q is true. So if you guys looking here, there's logically this P implies Q and not P or Q is logically equivalent, because if you guys looking here in this column is true and column where it says that not P or Q is true. So P implies Q here is false and not P or Q is false. So and we're looking the same here is a true and true. So you're looking here is true, and the last one is a P implies Q is true and not P or Q is true. So here we said that the two molecular statements P and Q are logically equivalent provided P is true precisely when Q is true. That is, P and Q have the same truth value under any assignment of the truth values to their atomic parts. To verify that two statements are logically equivalent, you can make a truth table for each, check whether the columns for the two statements are identical. And we're looking here that their columns, the two statements, they're all identical here. We says that not matter what P and Q's are, the statements not P or Q and P implies Q, so not P or Q and P implies Q, either both true or both false. So here you guys looking here is either is true or both. If either both is true or both is false. So here there is true, and you're looking here not P or Q is true. We therefore say that these statements are logically equivalent. So now we have proven that these two statements here, P implies Q and not P or Q, is logically equivalent. Alright, so now we're moving ahead with logical equivalence. So we're looking for R statements. It will not rain or snow, and it will not rain and it will not snow. Logical equivalent. So we're going to see here it will not rain or snow and it will not rain and it will not snow are logically equivalent. And what do you guys think? We're looking here. Solution, we want to know whether not P or Q. So here it will not rain or snow is not P or Q, so it will not. If you guys look in here, we look for P for rain and Q for snow, or in between here, so it will not rain, not parenthesis open, P or Q is logically equivalent to not P and not Q. So we say that it will not, that's a not, rain or snow, P or Q is logically equivalent to not P or not Q. So it will not rain and it will keep in mind there is or and this and, but there is they both equally equivalent, because it will not rain or snow and it will not rain and it will not snow is both of them is going to be logically equivalent. So we're going to make a table here. So our table is got a PQ, and if you look at here is not a P or Q, it will not rain or snow, and it will not rain and not snow. So there is, keep in mind there is two of them is equivalent. So we have our two T's here, two F's here, and the Q is here TF TF. So now we're looking here at not rain or snow, and not rain and not snow is going to be, both of them is going to be false false, and here false false, and here false false, and here is true true, because both of them are logically equivalent. So if you guys pay attention here, so and if you guys pay attention here, so this guy here, it goes here, and you can put it, it will not rain or snow, which is not P or Q, and here it will not rain first of all, and this one goes to the end, and it will not snow, which is this guy here, not Q. So we'll have observed here that both of them, they all matching with each other. So if you're looking here, they're all matching with each other, and they're all logically equivalent. All right, so we're gonna clear the screen. Since in every row the truth values for the two statements are equal, so if you're looking here, the truth statements are equal, the two statements are logically equivalent. So because the two statements here are logically equivalent, in plain English, it will not rain or snow, and it will not rain and it will not snow, is both of them is going to be logically equivalent. Notice that this example gives us a way to distribute a negation over a disjunction. So the first disjunction is an or. We have a similar rule of distributing over conjunction, which is and. So don't worry about this and. So we're looking for the or. We have distributed this one with or. If you're looking here, if it will not rain or snow, you guys can put it in another context too. In another, say in the weather, or you guys can do it with the train, or I will not go with the train or car, I will not go with the train, and I will not go with the car. So it is going to be, both of them is going to be equivalent because we're distributing here. So if you're looking here, that we mean the same thing. I will not go with the train or car, and I will not go with the train, and I will not go with the car. So we're going to distribute this one a negation over the disjunction, which is or. The first one disjunction which is or, and we have a similar rule of distributing over conjunction, which is and over here. And as I said to you guys can do it that I will not go with the train or car, and because we couldn't put it, we're going to distribute it with the disjunction or. And I'm going to say another ones, I will not go with the train and I will not go with the car. Then I'm going to use and. It's going to be conjunction. Now we're going to see De Morgan's law, and if you look in here, not P and Q is logically equivalent to not P or not Q. So as we said before, that we are not going with the train, our car is logically equivalent to if you are not going with the train or if you are not going with the cars. Alright, so the second De Morgan's law says that not P or Q is logically equivalent to not P and Q. So keep in mind, if you look in here, we have and not P and Q is logically equivalent to not P or. So here is or, that's or, and here is not P or, because this is quite opposite to this one, is logically equivalent to the not P and Q. So keep in mind they are quite opposite to each other, but they cover the both domains of not P or and Q is logically equivalent to not P or Q. So here in the parentheses here, we not P or Q is logically equivalent to not P and not Q. So this is a De Morgan's law. De Morgan's law do not directly help us with implications, but as we saw above, every implication can be written as a disjunction. So now we're going to see the implications or disjunctions. And the first one is we're going to see P implies Q is logically equivalent to not P or Q. So now we're going to give you example. If a number is a multiple of 4, then it is even, is equivalent to a number is not a multiple of 4, or else it is even. So if you're looking here now with this one in De Morgan's law, you can take any statement and simplify it to the point where negations are only being applied to atomic propositions. Well, that now we're going to say it's actually not, because you could get multiple negations stacked up. But this can be easily dealt with double negation. So if you look in here, when you guys are going to see this double negations as well. So negation not P is logically equivalent to P. So this not P is logically equivalent to P. So it makes sense, because not P is logically equivalent to P. So we can solve everything with a double negation. It says that now we're going to give an example. It is not the case that C is not odd. Means C is odd. So if you guys observe here, we have a double negation. Not P is logically equivalent to P, because we are applying two nots and they cancel each other. We're going to say that then it's logically equivalent to P. And it is not, that note comes here. So this note comes here. This is not the case that C is not odd. So this another note comes here. It means C is odd. So if you look in here, then if you guys going to see, it is not that the case that car is not old. So we're putting another negation here. Car is not old. It means that it's not the case that the car is not old. It means car is old. So that's how we're gonna prove that double negation not P is logically equivalent to P. So now we have so far we have learned some tautologies, and I'm gonna put it some tautologies, P or not P, law of the excluded middle. So if you guys look in here, if you guys anywhere here, some list of tautologies, the tautologies they are true in every case. So P or not P is the law of excluded middle. And the next one is going to be not P, and not P here is contradiction. So they're contradicting each other. And here double negation, we have not P, if and only if P is double negation. So here we have P and Q implies P, decomposing a conjunction. And here is P and Q implies Q, decomposing a conjunction. So these two guys here decomposing a conjunction, even though here now you're looking here P and Q implies P, and the bottom one says P and Q implies Q. They're both going to be, now we're going to see that they're all decomposing a conjunction. So P or Q constructing a disjunction. So the top one was decomposing, and the bottom one is P implies P or Q constructing a disjunction. So here we are going to apply the same thing on the Q. We have applied on this P, and now Q implies P or Q constructing a disjunction. And this guy here, P, if and only if Q, if and only if, then we're going to open the bracket, and then we will say P implies Q and Q implies P, definition of the biconditional. So here there is a biconditional in both here. Now we're going to see that's the definition of the biconditional. And the bottom one here, this guy here is P and Q, if and only if, and that's also biconditional here, if and only if Q and P, commutative law of and, which is conjunction. So that's a commutative law of conjunction. P or Q, if and only if Q or P is a commutative law of OR, which is disjunction. And when we get to the advanced levels, then we go to, after few in future video, we're going to see what is commutative law, what is the distributive law. So we're going to see the commutative law, and we're going to see the distributive laws. So here we have a bracket, and inside one it says that P and Q and R, if and only if, that's biconditional again. Here P, if and only if P and Q and R is associative law of conjunction, or associative law for and. And that's a commutative law. If you guys look in here, we have both biconditional here, we have a biconditional here, and we have a biconditional here. That's associative law, because we're going to associate this one. And in the future, as I said, in future videos, we're going to go in depth about the commutative law and associative law. So here we have P or Q or R, if and only if P or Q or R is associative law of disjunction. So here we have not P or Q if and only if not P and not Q is De Morgan's law. As we said that we've seen De Morgan's law, as we have used the rain and we have used the car. So with the train and car, that we're gonna say that I will not go with the train or car, and here, and I will not go with the train and I will not go with the car. So that's a thing, that's a De Morgan's law. And if you guys gonna see here, they're gonna be, both of them is gonna be they're gonna be equivalent to each other. So not P or Q is if and only if not P and not Q is De Morgan's law. And we're going to see the other way around. We're going to see that one's or, and now we're going to see and here this one's and, then we're going to go or, and so not P and Q if and only if not P or Q is also De Morgan's law. Alright, so we have put some list of tautologies, and keep in mind all of them is going to be true in any case. So that's a tautology. It means that they're going to be true in every situation, in every condition. They're always going to be true. So there are a few just I mentioned here. There are more than this. So keep in mind, just like nearly 15 or so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. But keep in mind there are around 25 to 30 of these tautologies. So but I'll put only 14 because you guys know all of this by now. We didn't explain to you guys commutative law and associative law, and we're going to do so in future videos. Alright guys, that's it for this video. If you have any question or comment, leave in comment box. Otherwise, I'll see you guys in the next video, and bye.